Hello everyone and welcome to the lecture of the course Mechanical System Design, in which we are learning about design of machine tool gearboxes. In this lecture we will learn about finding number of teeth on gears. In the previous lecture we learned about how to determine the optimum structural diagram if number of structural diagrams are available with us. Number of structural diagrams are the output of number of structural formulae which we have derived in the process of calculating or designing a gearbox of a machine tool. In this lecture, first we will discuss about the guidelines to determine number of teeth on the gears of a gearbox. We will learn how to draw a gearing diagram which will help us in calculating number of teeth on the gear, and finally we will see how to draw a deviation diagram which will help us to understand whether our design is correct or not. First, let us see the guidelines of calculating number of teeth on the gear wheels and what is the rationale behind these guidelines. The first guideline is for a 20 degrees full depth involute system, number of teeth on the smallest gear has to be greater than or equal to 18. As we know from the text which we have learned in theory of machines, that this requirement comes into the picture from the point of view of avoiding the interference between the gears. The second guideline is in a stage, sum of number of teeth on a gear pair must be same. The reason behind this guideline is to maintain the center distance between two shafts. For this purpose, let us consider one stage which comprises of three gear pairs, which means there are three input gears having number of teeth T1i, T2i and T3i on them, and correspondingly we have got three output gears having number of teeth as T1o, T2o and T3o. The center distance between the shafts is A. Now we know right now, for example, if the second pair is engaged, then the pitch circle radius of T2i and pitch circle radius of T2o, the summation of them has to be equal to pitch circle radius of T1i and T2o. It should also has to be equal to the sum of pitch circle radii of T3i and T3o. If number of teeth and module is known to us, then the pitch circle diameter can be given by m into t, and the pitch circle radius will be mt upon 2, which means mt1i plus mt1o divided by 2 has to be equal to mt2i plus mt2o divided by 2, which has to be equal to mt3i plus mt3o divided by 2, which is equal to a, that is the center distance. So if we simplify this equation, we will get T1i plus T1o equal to T2i plus T2o plus T3i plus T3o is equal to 2a by m. This is the mathematical proof with the help of which we can state the second guideline. The third guideline is minimum number of the minimum difference between the number of teeth on adjacent gears in a change gear block must be 4. This requirement is to avoid clashing of addendum circles of gears during gear change operation. Let us try to understand this guideline. Consider the same stage which we have discussed right now. The change gear block is the upper one, which comprises of three gear wheels T1i, T2i and T3i. Mathematically, the guideline states that the difference between number of teeth, that is T2i minus T1i, has to be greater than or equal to 4. Also, T2i minus T3i should also be greater than or equal to 4. Why this guideline comes into the picture is, right now the second pair is engaged. If I want to engage the first pair, I will have to move this change gear block to the left hand side. Whatever we are showing in this kinematic diagram are the pitch circle diameters. This distance is the pitch circle diameter, whereas the addendum circle diameters will be slightly higher than these pitch circle diameters. Now, when I am moving this change gear block to the left hand side in order to engage the first gear, it may happen that the addendum circle of the gear T3i clashes with addendum circle diameter of T2o. In order to avoid that, the minimum difference between the number of teeth on T2i and T3i has to be 4. The fourth guideline is deviation between actual spindle speed from calculated spindle speeds must not exceed 10 into 5 minus 1 in percentage. Obviously, it is to achieve accurate spindle speed within permissible tolerance, and we will learn more about this guideline at the end of this lecture. The fifth guideline is axial spacing between two adjacent gears must be greater than twice the face width. The reason of this guideline is to have complete disengagement of the previous gear prior to engagement of next gear. It can be illustrated by the same diagram. Right now the second pair is engaged, and if we assume that face width of all the gears is equal to B, then if we are trying to engage the first pair, we will have to move this change gear block to the left hand side. In this case, if the distance between these two gears is less than twice the face width, then T1i will engage with T1o before full disengagement of T2i from T2o. And now this shaft cannot rotate with two different gear ratios, which will ultimately fail the design. In order to avoid that, the distance between these two gears has to be greater than twice the face width of the gears. If you see all these 5 guidelines, first 3 guidelines are very important as far as calculating number of teeth are concerned. Fourth and fifth guideline, especially fourth guideline, is there to qualify the entire design, and fifth guideline is not actually for calculating the number of teeth, but it should be considered while designing the gearbox in total. In the last lecture, we have drawn the speed ray diagram, which I have reproduced over here, and I have enlisted all the 12 speeds which we want to achieve at the output shaft. We have 2 more speeds. The NX is an additional speed equal to 346.41. It is the intermediate speed between N6 and N7. It is important because that is the speed with which the first shaft in the gearbox will be spinning. There is additional speed Nm, which is the speed of the motor, which is the prime mover in this gearbox. The first reduction, that is from Nm to Nx, will be achieved through the belt pulley and belt arrangement. So we will not be discussing much about that, but we can calculate the ratio of diameter, which is equal to ratio of these two speeds Nx to Nm. Let us go ahead with calculating the gear ratios first. If we consider the first stage, the Nx is the input speed and we have got 2 output speeds. The output speed N7 will be achieved by one of the gear pair. The gear ratio of this gear pair will be N7 by Nx. Similarly, another output speed Nx will be achieved by the other gear pair. The gear ratio of this gear pair will be N6 divided by Nx. So for calculating gear ratio of first stage, it is very simple, but it will go on complicated for the next stages. So we have to calculate these gear ratios systematically, and for that we have to calculate or we have to draw a diagram called as gearing diagram. I'm calling it as a calculated gearing diagram because we have to draw one more gearing diagram at the end of the design, which will be called as actual gearing diagram. We will understand the difference between them at that point of the time. Now, at first we will have to draw 4 shafts in the gearbox. There are 2 gear pairs, T1I T1O and T2I T2O in the first stage. We have to calculate the gear ratio for the first gear pair, which is equal to N7 by Nx. It should be noted that the ratio of teeth is inverse as that of ratio of speeds. I hope you are aware that number of teeth is inversely proportional to the speed of the gearbox. Therefore, if on the left hand side I am taking the ratio of input gear to output gear, on the right hand side I should have output speed upon input speed. It is very important to understand and should not be confused. So T1I upon T1O is equal to N7 by Nx, which gives me a value 1.12. Similarly, for the second gear pair T2I upon T2O, I have speed ratio as N6 upon Nx, which is equal to 0.89. In the same fashion, I have to calculate gear ratio of third and fourth pair by considering speeds in the second stage. Moreover, for the third stage, which means between shaft 3 and 4, I have 3 gear pairs, gear pair number 5, 6 and 7, and I can calculate the gear ratios in the same fashion. Once the gear ratios are known to us, we can go on calculating the number of teeth on each gear wheel. Let us start with the first gear pair. So the ratio is 1.12. Now this ratio is greater than 1, which means numerator is greater than the denominator. So this has to be a smaller gear. So let us assume T1O equal to 18, which is the first guideline for calculating the number of teeth. We will get T1I is equal to 20.16. Now this is the number of teeth, so it cannot be a fraction value, so we will round it off to 20. Here make a note that this rounding off error should be as low as possible. Here the error is only of 0.16, so I would say it is acceptable. You will understand significance of this rounding off error when we will be calculating the deviation in the speeds. At this point of the time, bear one thing in mind, that this deviation should be as low as possible. Let us calculate number of teeth on the second gear pair. The ratio is 0.89 from this box. Since the ratio is less than 1, the numerator is less than the denominator. This will be a smaller gear. So let us assume T2I equal to 18. We will get T2O equal to 20.22, which will be rounded off to 20. So we have already found the number of teeth, but let us verify them with respect to the guidelines which we have got. So the first guideline has already been met. The minimum number of teeth on the smaller gear are 18. Sum of number of teeth on a gear pair, that is 18 plus 20 is equal to 38, has to be equal. 18 plus 20 is equal to 38. So second guideline is also met. The difference between adjacent gears on the change gear block, that is T1I and T2I, should be minimum 4. Now that guideline has been violated, which means we have to recalculate it by considering or by assuming more number of teeth on the smaller gear. So instead of 18, we will assume now the minimum number of teeth as 20 on T1O as well as T2I, and we will recalculate and we will recheck whether all the three guidelines are met or not. And this is a trial and error process, so we have to keep doing on it. If we are not yielding proper results with the assumption of 20, we will go for 22, we will go for 24, and so on. I got satisfactory results when I reached to minimum number of teeth of 32. For that value, T1I is 36 and T2O is also 36. So this is already satisfying the first guideline. Minimum number of teeth should be 18. We have 32. Sum of number of teeth on a gear pair, that is 32 plus 36, 68. 32 plus 36, 68. So second guideline is also satisfied. Third guideline, that the difference between number of teeth on a change gear block, on adjacent gears on a change gear block, should be 4. We have 36 and 32. So the third guideline has also been met. So the first stage, calculation for the first stage, is over. We have to repeat the process for the second stage as well as third stage in the similar fashion. Only thing, we have to be careful in the third stage while calculating number of teeth on the sixth gear pair. Since the gear ratio is equal to 1, if we assume T6I as 18, we will get T6O also as 18. So although it is satisfying the first guideline, we have to see how many number of teeth the fifth and the seventh pair is having to check whether it is meeting the second and third guideline. Let us see it in the next slide. So I already calculated a number of teeth on all the gear wheels, 7 input gear wheels and 7 output gear wheels. We were talking about number of teeth on the sixth pair. So if we take 18 and 18 over here, I have already calculated T5I as 44, T5O as 18, and vice versa for T7I and T7O. If you observe, the sum of number of teeth on a gear pair in the third stage is 44 plus 18, which is 62. Here also it is 18 plus 44, so 62. Now if you assume T6I and T6O as 18, then the sum of number of teeth is 18 plus 18, 36. So it violates the second guideline. To sort it out, the way out is very simple. Add this number of teeth, 44 plus 18, that is 62, and straight away divide it by 2. It comes out to be 31 and 31. So we are able to meet all the three guidelines properly. So this is how we can calculate number of teeth and on all the wheels of the gearbox. So the design is over, but we need to verify, we need to calculate the deviation. So first of all, we have to understand from where this deviation is coming into the calculation. These are not the exact number of teeth which we have calculated. If we remember, we have to round it off because number of teeth cannot be a fraction value, which means with this actual number of gear teeth, the gear ratios are not exactly same. There will be slight variation in the gear ratios now. So we have to calculate the gearing, we have to draw the gearing diagram once again by plugging the actual gear ratios from this number of teeth in this fashion. Now this is the actual gearing diagram, which is calculated by considering number of teeth. The gear ratios are calculated by considering the actual number of teeth. Fortunately, the rounding of errors were small when we have calculated this number of teeth. So if you compare this actual gearing diagram with the previous, that is calculated gearing diagram, you will see the only difference is in the first block. The calculated gearing ratio over here was 1.12, whereas in this actual gearing diagram it is 1.125. However, this is definitely going to make some difference on the final output speeds which we are going to get. So let us calculate these actual output speeds. Now observe carefully how to calculate these 12 speed steps, 12 output speeds. We know the first shaft is going to spin at 346.41 rpm. In the first stage, if we engage the first gear pair, the second shaft will spin at 389.71 rpm. If we engage the second gear pair, the second shaft will run at 308.3. Now if the second shaft is spinning at 389.71 and we engage the third gear pair, we get 487.13 rpm on the third shaft. If we engage fourth gear pair with the same speed on the second shaft, we get 311.76 rpm. However, if the second shaft is running at 308.30, which means the second gear pair is engaged, and in the second stage, if the third gear pair is engaged, we will get 385.37 rpm. Similarly, if the fourth gear pair is engaged, we will get 246.64 rpm. That means we will get 4 speeds on shaft number 3, which can be correlated with what we have drawn in the structural diagrams and speed ray diagrams. You will observe there are 4 points on the third shaft in those diagrams. Now for 487.13, if I engage 5th, 6th and 7th gear pair one by one, I will get 3 output speeds on the 4th shaft. Similarly, if I spin the third shaft at 311.76 rpm and engage these 3 gear pairs one by one, I will get 3 more speeds. If the third shaft is running at 385.37 rpm and I engage these 3 pairs one by one, I will get 3 more speeds. And lastly, if the third shaft is spinning at 246.64 rpm and I engage these gear pairs one by one, I will get 3 more speeds. So these are the 12 actual output speeds which I got on the 4th shaft. Now obviously, since there was a slight variation in the gear ratios, there will be variation in the output speeds as well. And now I have to check whether this variation, which is called as deviation, is acceptable or not. This is the last step of qualifying our design. The percentage deviation is calculated by the formula actual speed minus calculated speed divided by the calculated speed into 100, and it should be less than 10 into phi minus 1 percentage, where phi is the geometric progression ratio of this gearbox, which we had already calculated as 1.25. For this purpose, I have already filled this table. It has got speed steps in the first column, 12 calculated speed steps, then 12 actual speed steps, and the percentage of deviation has been calculated by using this formula on this slide. Then you can observe some of the values are positive and negative. It depends upon whether the actual speed is more or less than the calculated speed. The last column is the limit, which is calculated from this second formula, 10 into phi minus 1. So phi is 1.25. So from that we get this value. It can be observed that for all speed steps, the percentage deviation is within the permissible limit. The same thing has been depicted in this graph. This graph is called as deviation diagram. On the x-axis we have spindle speed steps. On the y-axis we have deviation in speed expressed in percentages. This blue curve is the percentage of deviation and these orange curves are the permissible limits, and it can be observed that the deviation for all speed steps is within the acceptable limit, and therefore the design which we have been doing from all last 5 lectures is acceptable. So the design is acceptable and completed at this point of the time. The one question which may come in your mind is what happens if the percentage deviation is not within the limit. Now you must remember one thing which I talked about while calculating number of teeth on the gears, that try to keep the rounding of error as low as possible. If the rounding of error is very high, something like 0 0.4, 0 0.5 or zero point 0.6, then you should assume higher number of teeth on the smaller gear and recalculate the number of teeth on the other gear in the same gear pair, so as to bring this rounding of error to minimum, because the rounding of error gives rise to the variation in the number of teeth. Variation in the number of teeth gives rise to variation in the gear ratio, which ultimately gives rise to variation in the actual spindle speed. So we have to take this care at that stage only, so that we don't have to go into the recursive loop of calculating number of teeth again and again. So be careful at that step only. The second question that may arise out of curiosity is typically machine tools have got large number of speed steps. Right now we calculated a gearbox which is having 12 speed steps. We can have 18 speed steps, 24 speed steps, but we don't observe so many speed steps in automobile gearboxes. So you should note that the machine tools, typically lathe machines, are made up of prime movers, which are electric motors which are running at constant speed. Therefore, in order to achieve different speeds, to keep the loss of economic cutting speed minimum, we require so many speed steps. Whereas in case of automobiles, the prime movers are engines, which are variable speed prime movers, and therefore the prime mover itself is capable of achieving different speeds. So we need gearbox over there, not just to have variable speed, but to have different torque, range of torque and range of speeds, which can tackle different terrains. So the purpose of having gearbox is slightly different in machine tools and automobiles, and that's why we don't see the so many speed steps in the automobiles. However, if we observe some of the modern automobiles, they have got automatic transmission which is capable of shifting the gears very quickly, and it can handle a lot of data. So there are 10 speed transmissions as well, but they are automatic transmissions, and there the philosophy is quite similar to that of gearboxes of a machine tool, where the engine keeps running in a very narrow range of the speeds, which is perhaps the best speed to achieve the highest fuel economy and lowest emissions. And that's why nowadays you will see similar trend being followed in the automobiles, that in order to keep engine running within a very short range of speeds, they use lot of speed steps, something like 9 speed step, gearbox having 9 speed steps or 10 speed steps, and so on. So that's all from my side as far as design of gearboxes of machine tools are concerned. Thank you.